I'm going to tell you about a bijective function that establishes that all Collatz sequences must be finite. I'm not saying must end in 1, although that is the implication, but what it establishes beyond a shadow of a doubt is that all sequences are finite. And this bijective function is a mapping between numbers of a certain form, 8n plus 5, with every odd number, 2n minus 1. And mathematicians have really made a mistake by ignoring this, and maybe they just didn't see it. I will get to that possibility after showing you what I'm talking about. So you can create a graph of the outputs of each input-output operation in the Collatz map. And it behaves like this. There's 3 tiers of numbers, as you can see in the graph. And the diagonal line is a representation of all the odd natural numbers. So the numbers that are shown should be understood in relationship to the numbers that are not shown on this diagonal line. But I will show you how they apply in just a moment. So all numbers of the form hm plus 5 map to the set of the odd natural numbers. Well, how? And well, the way they map is using this operational function, n minus 1 divided by 4. And really this is what precludes infinitude. n minus 1 divided by 4. So you see that these numbers beginning with 5 and separated by 8 are obviously infinite, 5, 13, 21, 29, and so on. And these have a mapping to every odd integer. So 5 minus 1 divided by 4 equals 1, 13 minus 1 divided by 4 equals 3, 21 minus 1 divided by 4 equals 5, and so on. So this is a really nice example of a one-to-one mapping, a bijection, and both of these sets are of equal cardinality. And that's important because there can be no exceptions to this rule. 2 other mappings, which are subsets. And so whereas this is a bijection, the other 2 are injective. So the first injective function is for numbers of the form 8n plus 1, and the operation is n minus 1 multiplied by 3/4 or 0.75 plus 1. This produces a whole number. Oh, again, these numbers are 8 apart, beginning with 1. And the outputs are, as you see, input 9, output 7, input 17, output 13, input 25, output 19, input 33, output 25, and so on. And the second bijective function is for numbers of the form 4m plus 3, and these represent every other odd number. The mapping function is n plus 1 multiplied by 3/2 or 1.5 minus 1. And the result is this. So input 11, output 17, input 15, output 23, input 19, output 29, and so on. So we see the output is separated by 6. So obviously, again, this is a subset, an injection. And in contrast to the first case, which is a bijection, meaning there's a one-to-one mapping, all the odd integers are accounted for. The second two cases, the injective cases, create mappings that overlap entirely the first case, the bijective case, except for multiples of 3, which only exist in the bijective case. So why don't mathematicians see this? Well, the n-1 divided by 4 operation is actually hidden pretty comprehensively in the 3x plus 1 function. It's as if it doesn't exist, and this is because it's formulated as an even-odd function. Well, this is what I'll try to explain. So if you multiply any odd integer by 4, obviously the product n has at least 2 factors of 2, regardless of what the original number is. So when you multiply 4m plus 1 by 3m plus 1, like this, n times 4 plus 1 times 3 plus 1, you have the 4m plus 1 result, and then you have 2 more factors of 2. And thus divisions by 2, there's 2 even steps you will see in even-odd sequences, and you do not have the original n in the even-odd continuation. That original n is missing, and this makes it look like a different sequence. So what this means is you may consider this continuation to be a branch or a merge. And this property must apply to every odd n, because every n can be subject to 4m plus 1. You can always multiply a number by 4 and add 1 in every case. Now, so let's take an example of a sequence 31, and you multiply by 3, add 1, and then divide by 2, and this one gets to an odd number after 1 even step. Now, the other way to look at this is sequence to sequence. So this is where n times 4 plus 1 multiplied by 3 plus 1 comes in. So 31 times 4 plus 1 actually produces a merging sequence. Notice that 31 and 125 merge on 94, and the following odd number is 47. Then you multiply 125 by 4, add 1, get 501, and this goes through 5 even steps before ending, not ending, but reaching 47, the first odd number. And you will see the actual merge occurs on 376. So what needs to be observed is that 31 is not present in the sequence 125, and 31 and 125 are not present in the sequence 501. So this makes the 3 sequences appear to be different. However, it is quite obvious, plainly obvious, that they are indeed the same. And this is the basis for my contention that all sequences must be finite. There can be no exceptions.